All right, in the last video, we talked about what a Markov chain was, and we ran through an example, but really doing it by hand like that was a bit more involved than we would like to, and we could imagine how hard it would be if we had to try to predict the behavior 20 elections down the road. So let's try to get some bit of linear algebra involved. So definition 3.5.2. We'll be defining the transition matrix and the state vectors of a Markov chain. So assume that we have a Markov chain with m states. The transition matrix of this Markov chain is the matrix P with entry Pij, where Pij is the probability that we go from state, and this is a bit backwards from what you would do naturally. So from state J, so the column determines where you start, to state I, and the row determine which states you land in. This is just to make sure that we can multiply by the vectors on the right, not the left. All right, so the state vector is x, x1 through xm, where xi is the probability that we are in state I. All right, so a vector in general from x1 through xm is called a probability vector if the sum of its components, so x1 plus x2 plus xm, equals 1. All right, so let's see how this setup helps us answer questions like we just answered in the first example. So assume that we are currently in state vector x0. So the odds that we are in each state is inside a vector like this. After one more iteration, we'll be in vector x1, which is p times x0. And after n iteration, we'll be, well, you apply p each time, so you'll be in p to the n x0. All right, so you can see how our knowledge of powers of matrices and our technique to compute them could be helpful here. Part 3, every state vector is a probability vector, and the sum of the entry of each column of P is 1. All right, so before we prove this proposition, which we'll do next, I want to do an example just to give you a sense of what the probability matrix is, the transition matrix. So let's look again at the example that we looked at before with conservatives and liberal, 85%, 15, 10, and 90%. Give the transition matrix of this Markov chain. All right, so we have two states, and so P is going to be a 2 by 2. The columns determine the starting state. So this is the start. We could start liberal or we could start conservative. And then the row is going to tell us where we end. We can end liberal and end conservative. And the entry that I'm going to put in this box, that would be P11. That's the probability of going from liberal to liberal. All right, so that's this arrow here. You stay liberal, that's 85%, so I'll write 0.85. And then the next one over, this entry here is the probability of going from conservative to liberal. And so that one is going to be 90. Conservative to liberal, that's 10. Sorry, wrong number. All right, and we keep going like that. So this one would be the probability of going from liberal to conservative. That's 0.15, and then conservative to conservative. So that's 90. All right, so notice that we can see this one. The sum of the entries in each column is 1. here we have 1, and here we have 1. That's because if you're liberal, you're either going to go back to liberal or you're going to go to conservative. So the sum of all those possibilities, those are all the possibility for somebody that starts liberal, has to add up to 100%. All right, so we'll say that in the proof next. All right, let's recompute the two questions that we had in the last page. If you start liberal, what are the odds that you go conservative? So if you start liberal, your current state is 100% liberal. So liberal 100%, conservative 0. You know you're a liberal at this point. And so after one election, that's x1, that's going to be p times x of 0. So I'm going to take p, and I'm going to multiply it by 1, 0, and I'm going to get up, so 0.85, 0.15. So the odds that they will vote conservative, that's this one. In fact, I mean, it also keeps track of what are the odds that you're going to vote liberal. All right, now if we want two elections, then we want P2, X2, that's P2 times X0. So I'm going to take this P1 times X0 and multiply it by P again. So I'm going to multiply by 85, 10, 15%, and 90%, 0.85, 0.15. I'm going to get 0.85 squared plus 0.1, 0.15, and then here I'll get 0.85, 0.15, plus 0.9, 0.15, and so I'm going to get, sorry, it is a bit low on space, I'll put it over here. That's going to be 0.7375 and 0.2625. All right, so 26.25% chance of voting conservatives into election. Notice, let me take this. Let's compare it to what we've done before. If you notice, that computation is exactly the one that we had here. So we got exactly the same answer. Of course, we did a few other computations. We also computed the odds of voting liberals into election. Actually, let me erase this before I forget. We also have the odds of voting liberal. Of course, because there are only two possibilities, you know that's 100% minus this one. But if you had multiple possibility, if you had 4 different states or 5 different states, then you would keep track of all the probability at each step. And that's part of the reason it works so well. All right, so let's prove that proposition. So I want to prove this proposition. I want to prove that if we are in a state vector x0, after one iteration we'll be at p of x0. Let's prove that. All right, so assume that x0 is a1, a2, am, and x1 is b1, b2, bn. All right, so we want to prove that that x1 is px naught. All right, so we'll just look at one entry. Let's look at bi, and let's just figure out what that means. So bi, that's the probability that x1 is at state I. So I could have come from any of these states. So I could have come from state 1 and then moved from 1 to I. Or I could have come from state 2 and then moved from 2 to I, and so on up to state M, and then probability that you go from M to I. All right, so let's see what all of these entries are. So x0 is at 1, that's A1. X0 is at 2, that's A2, and so on. Then going from 1 to I, you start at 1. So if you remember, where you start is the column. So the column is where you start. So that's 1. And then you end up at I. So row I, column 1 of the matrix P. And then A2, P, I2, AM, P, I, M. All right, so let's check whether that matches what we would get if we multiply P by X0. All right, so let me write out what P is. It's P11, P12, P1M. And then the row I'm interested in the most is I, because those are the entries I see here. So hopefully those will be the ones that I'm using when I'm trying to compute BI. All right, so this and then PM1, PM2, PMM. All right, and I want to multiply this by A1, A2, AM. All right, let's look at the entry in the ith. Actually, I'm going to need way more room than this. Let's look at the entries that I have in the ith row. All right, so actually, let's look at the first one as well. So first one, I'm going to get this product. So I'm going to get A1 P11 plus A2 P12 plus AM P1M. All right, so that's equal to this when I equals 1. So it's B1. And then the middle one, I'm going to get this times this, and that's going to give me A1 PI1 plus A2 PI2 plus AM PIM, and so that is BI, and so on. And so yes, we do get X1. But what's nice now is I can actually prove this, that if I'm looking for what happens n iterations down the road, then I could just multiply by Pn. So it follows from applying 1 multiple times. So xn would be P times xn minus 1. And that'd be P squared times xn minus 2. And you keep applying P until you get to 0. And notice that the sum of the powers gives you n, so it's going to give you p to the n. All right, let's see. Suppose that xn is A1am. I want to prove that I want to prove that it is a probability vector. So A1 is the probability that xn equals 1, and am is the probability that xm equals 1. Sorry, I said x1. Sorry, xn xn equals m. All right, so if I have all of these and I add them up, it's like adding the probability that xn equals 1 plus the probability that xn equals 2 and so on, plus the probability that xn equals m. It has to be one of them, and so that's 100%. It has to be one of these values. That was the first condition of a Markov chain. There are only m values for each state, and so that's 1. All right, finally, the last thing I needed to prove, I need to prove that the sum of the entries in each column of P is 1, just like we saw here. All right, so let x0 be EJ. All right, so that means you know you're in state J 100%. Then if I multiply P by x0, I'm going to get x1. But that's P times EJ. And you remember we used that recently, that if you multiply a matrix by EJ, you get, well, let's see. Uh, 1M, M1, MJ, MM. And so you will get, oh, sorry, 0, 1, 0. And so what I'll get, when I multiply these, I'm going to get P1J, and I'm going to get PMJ. And so this is a probability vector. So this is a state vector. And so it's a probability vector by what we just proved in 3. And so that means P1J plus PMJ. That's equal to 100%, which is 1. All right, good.